folks, welcome back. So we've got this pretty mysterious looking formula. I really wish I knew more physics. Like if I could take a class right now, I would take a physics class so that I could understand what's going on here. I think there's something really nice that this formula is doing, and I wish I could understand it more. I just don't know enough physics to tell you why it works. So I will tell you the sort of mathy version of why it works, and hopefully after class some physics people come and explain it to me. Okay, so we've got this formula. We want to calculate out why this actually holds, what's actually going on here. So I want to focus our attention on just two terms of the formula. Okay, so we'll just stare at these guys for the time being, the F1 terms. Okay, and I will try and argue for you that the integral of this guy should be the integral of this guy. So our claim Okay, so I've written down a pretty scary looking definition of this region, right? This is sort of, lots of formulas and stuff coming out of nowhere. What this specification of the region is doing is saying that our region is bounded by two graphs. So that our region D looks something like this. So given a region bounded between two graphs, and we can show that this integral is equal to this thing. Okay. So this is a pretty mild assumption on our region. Okay, so I've sort of said several times that this is like fundamental theorem of calculus, right? Integral on region is integral on boundary. We're going to see that the proof of this part of Green's theorem heavily uses fundamental theorem of calculus. Okay, so we'll work with the left-hand side. So we've got this integral over the region D, and we can choose what order to integrate things in. Right? We can choose to say that this is something that we're integrating in dy, that will integrate y first. Okay, now, our bounds for the x are between a and b, and our bounds for the y are between g1 and g2. Okay, the fundamental theorem of calculus says that this derivative and this integral should cancel out. Right, so the fundamental theorem of calculus says that we should get here. So we undo this derivative operation, gives us f1, no partial derivatives. Okay, and now we can use those upper and lower bounds. Yep, sure.
One question. So like when in integration you take out the minus and you usually change the bounds. But if here is remove of the minus first and then use the bounds.
Right, so here I'm just keeping the minus out front. I'm just holding on to the minus sign the whole time. Okay, so this gets us to an integral in x. Okay. And we could equally well think of this as sort of being some kind of parameter or some kind of time variable. Okay, so we've done the algebra on the left-hand side, and we've got to a place that looks like this. Okay. Now I want to look at the algebra of the right-hand side of this guy. So we'll do a similar calculation working on the right-hand side. Okay, and for that we need to parameterize our boundary. So the first thing we notice is that we need counterclockwise orientation, right? So we need to have counterclockwise guy here. So we're going along in this direction, up, back, down. So our parameterization going along the graph of g1 of x and along the graph of g2 of x. And we're going between a and b. So when we integrate, we plug in our x coordinates. So that's following along this guy. So when we go in this direction, t increases from a to b. And now when we go in this direction, we decrease from b to a. So we get here. These are starting to look really familiar somehow. Right? Here we've got F1, G1, F1, G2. Here we've got F1, G2, F1, G1. So the only thing we're missing is that there's no minus sign out front here. I'll take away the minus sign out front.
So there we have F1 and F1. You can switch to F1 and F2.
Oh, sorry, F1, yeah, both. So these two integrals must measure the same thing, right? Here we've got F1, G1, F1, G2, F1, G1, F1, G2. The only difference is that our variable names are different. Right? Here we're parameterizing with t, here we're parameterizing with x. So I guess we get these guys measure the same thing. that is very nice. This is probably the most proofy thing we've done the whole course. If there's things you'd like to know more about, please ask. Yes, sure.
How you from the last step to the last step?
This guy here?
Yeah, the minus.
Right. So we multiply this guy in. Right? Minus by minus is plus. The reason for this we will not discuss. So we minus by minus gives us this guy plus. And then we get a minus guy out here.
So you had a tab like that goes on G1 of x and then G2 of x.
Yeah.
What about these vertical lines?
Aha, right, yes. Yeah, there's a good point, right? That this path just jumps. Ah, so we go da 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 da, and then suddenly we're here. Right? Notice that here, right, x is constant. Right? So here we're just going straight up and down. So along that part of the path, dx will be 0.
Would that last point help to explain why we often get a bunch of zero?
Yeah. So there's a good observation from the front row. We earlier in lecture, right, we saw that those vertical parts contributed 0. So whenever we've got a vertical line, dx will be 0. Whenever we've got a horizontal line, dy will be 0. Yeah, so that's why we got all those dx's and dy's being 0 earlier.